Hi everyone. So this is a live stream and today we'll be doing some malware analysis. But before that, a little about Redfox Security. So Redfox Security is a cybersecurity firm which provides penetration testing services in various domains of cybersecurity, and we also have some amazing courses, course material and study material available on academy.redfoxsec.com. Moreover, our YouTube channel, the one which you are on currently, is heavily and very densely populated with a lot of free content and a lot of free resources which you can utilize to maximize your learning potential. So let's get on with today's topic, which I think you guys already know is WannaCry. So a little background on WannaCry. In I think about 2017, this ransomware hit a lot of computers in the world, and this was a very big issue because it was locking out and spreading like wildfire, right? And it was encrypting files left and right, and it was very difficult to stop this. The person who was accredited to finding out the kill switch is a person called Marcus Hutchins, and what we are gonna do today will actually mimic what he did or he potentially did when he was debugging WannaCry. Moreover, what we're gonna try to do is understand how this particular executable is working and what all indicators is it giving, right? So host indicators or network indicators. We'll go through some basic static analysis, so a little bit of dynamic analysis. We'll dissect the binary apart. We'll do some decompilations, and we'll also then head into debugging, and we'll try to get some live interactions with the binary, right? So let's get started. My favorite tool to start malware analysis is peStudio, right? But the thing is, before getting into malware analysis, why not just detonate the malware, right? So before detonation, again, we need to have a sandbox so we don't actually encrypt something or destroy something that's important to us. So as you can see, I right now am inside a VM. Moreover, this VM is not connected to the internet or any other device, and it's on a host only adapter. And since we're detonating this, whatever the state of the VM will be after detonation will be useless because everything will be encrypted. So I have created a snapshot called WannaCry in which I have this open, right? This particular desktop setup, like WannaCry is right in front of us, ready to detonate. So let's detonate WannaCry and see what it does. Okay, yeah. Okay, we see something on the desktop, a .txt. I'll not touch anything right now. We'll go over this in a while. Let it detonate completely, and then we'll see. Okay, there we go. So the malware has successfully detonated. I think it's still going through some phases where it's encrypting everything, right? Because I see a few files which have not been encrypted yet. But basically, we have this huge pop-up, and it's telling us that all our files have been encrypted, and we can recover our files if we pay $300 worth of Bitcoin to this particular address, right? So let's just go into some random directory and see what the status is of the files there. So what we see is that the license.txt files over here, or the changelog files, they have a new extension called WannaCry. and we can't really open that kind of a file. What we can try, because if it's just an extension, then who is bothered. We can try to open it with something like Notepad++, and there we see that nothing is making sense, right? Everything is gibberish. So we can't really use this file anymore. Whatever it had before, now it does not anymore, right? We can go further inside. Okay, so like these files are still okay, I guess. They have not been, yeah. So WannaCry has not reached these files yet. Maybe it won't. We've just detonated it. So let's move over to some other directories. Do we see anything else? Let's go into tools, okay, so these are just executables. They won't really have anything to there, but we have a txt telling us that the important files are encrypted. Now the thing is that it says important files, and the malware, what it does is it actually has some sort of logic for finding some particular extension files which it considers important to you. So as you saw, that .txt file did get encrypted. However, the .exe, my bad, yeah, the .exe is still there. The readme.md file is still there, right? So it must have some logic. Anyhow, we've had that detonation, really fun. Now let's move on to the actual analysis. So for that, I'll just restore the snapshot. What this does is, this process, it actually speeds up the process of malware analysis, because I can keep going back to the snapshot and detonating it again, because to collect indicators, I have to detonate it again and again when we reach dynamic analysis. As far as static analysis is concerned, peStudio is something which I consider a very, very potent and powerful tool. Okay. So we have fed peStudio the file. It's going to take a while and analyze it properly, look for indicators which will range from static, just signature, like just SHA-256 hashes, to what kind of libraries that this binary is loading and stuff like that. Okay. And what we can do to confirm some of the stuff, because peStudio is not, because this device is not connected to the internet, once it calculates the SHA-256, what I'm going to do is I'm going to just put that into VirusTotal, because that is one part of the process, right? When you have a malware sample and you don't know what it is, ideally you should take a SHA-256 hash and put it on VirusTotal to know if this is an existing malware or something of the sort, right? So I'll let that run. Meanwhile, something that we can do is gauge the capabilities of this binary. If you're curious about what kind of a VM I am in, it's called Flare VM. It's basically I won't say a flavor, but basically Mandiant made this script which converts your virtual machine into a malware analysis and triage workstation. So this is that particular script has been used on the VM. You don't run that on your host, you run that on a VM only. Okay, it's lagging a bit because peStudio is very resource heavy. Yeah, so there is another tool which is released by Mandiant. It's called Kappa, I think. That's how you would pronounce it. But basically, it gauges the capabilities of the binary, whatever binary you present to it. So let's give it WannaCry.exe. Even this is a bit resource intensive. I'm not sure if I should have run both of them at once because in the end it's a VM. But I think it will go through. And in the background, peStudio has already collected a bit of the information. So it's a 32-bit executable. Its description is disk defragmenter, which is, I don't know, very weird. The original name is this random string. All right. So, it's malware, right? But why would it have a description like this? Right? That is one question that comes to my head, and I think it's mostly there to just blend into other applications, other executables on your device, right? Okay, so Kappa is done. It has listed a lot of capabilities for this binary. Now note that if you run Kappa on any binary which actually performs legit HTTP communication or legit stuff, even then Kappa may consider that to be, let's say, HTTP communication, it would list it like this, or maybe C2 communication. The thing is that when you run a tool like Kappa, you're most likely thinking about malware analysis, malware triage. So I think it's more of the fact that what Kappa will do is it will assume that you're dealing with some sort of a malware or something malicious, and it will nitpick literally everything malicious that it can about that binary. Okay. So we have obfuscated files or information, file and directory discovery, system information discovery, system network configuration discovery, shared modules, C2 communication, lots of stuff, socket communication, HTTP communication. Now we can keep noting all these things down because later when we collect dynamic indicators, we will actually see the malware trying to do some of this stuff. Receive data, send data, connect to a URL, create UDP socket, terminate process, run as service, create service, modify service. So yeah, right, we can keep a track of these things because these things they will raise some red flags, and they should raise red flags. So this is something that we will keep in mind. And it also has a few capabilities linked against zlib, which I'm not really sure about. So we'll still keep these things in mind. It also potentially has a persistence mechanism. Alright. Okay, so I think peStudio is done because the computer suddenly sped up a little. So let's go to the indicators section. It has signatures listed as being flagged. So I think that is something which should raise a lot of red flags, because if the signature is being flagged, that means this malware has potentially been seen before. Socket libraries being imported, IP helper API, internet extensions for Win32 library. We have a lot of flags on the imports, so we can take a look at that. Now I think looking at the imports, you can get a pretty decent idea about what the malware might try to do, because as you can see, and as we will see, and as we have already seen from the Kappa tool, that it might want to create a service, which we can see from the import here. It might try to do some HTTP communication, internet open, right? And change service configuration, maybe some persistence, maybe we're talking about persistence or something like that, right? And we like, my favorite thing to do is sort these by different these columns. We can look at all the groups: open SC manager A, close service handle, start service, open service, load resource, find resource, internet open A, create file. It's going to probably, as we saw, it creates files, right? So we have all these imports over here, and we can also look for the technique. Crypt gen random, crypt acquire context. See, in the end, it's a cryptor, right? It's a ransomware, so it's probably I think something expected to see something like this here. Otherwise, we can also look at type. Okay, everything is implicit, I believe. Ordinal. Okay, so we have some connect, close socket, receive, send, socket connect. So those socket connection things, we can see them as imports. String suspicious. It has some suspicious strings. Let's go and take a look at strings. This is going to take a while because it has a lot of strings. Let's look at the flagged strings. Okay, so most of these are the imports which we already saw, right? Crypt, gen key, crypt, decrypt, crypt, encrypt, destroy key. Wow, so like what we can see from here is it's gonna encrypt stuff and then destroy the key. Very fun. Anyhow, we can also sort this by what section it's in, right? And we can also sort it by if it's listed in a group. See, this is a big binary, so it's natural that you can't go through literally everything. What I find very interesting, at least with this binary, is the DOS stub. I think we saw the DOS stub right here somewhere. Because there is not just one DOS stub over here, there are multiple. How do I see that? And the fact is, if there are multiple DOS stubs, you can assume that there are multiple binaries within the binary, right? It's a pretty good possibility. It's something that you can probably guess. DOS stub. Okay, DOS message. So we have 4 DOS messages over here. One DOS message would be for WannaCry, and then we have 2 DOS messages in .data and one in .rsrc. So I would bet that this has more than 1 or 2 executables inside of it, right? Let's go back to the indicators. So yeah, a lot of strings have been flagged as suspicious. We have a URL pattern which is flagged as suspicious, a little suspicious, because it may just be legit, but this is like a very weird URL. This is gonna come back to us when we start with dynamic analysis. But this is more or less what the basic static analysis is going to be about, because I really want to detonate this malware again, right, and see what it actually does. So we can go through literally every one of these in heavy detail, and that may help us find out what's gonna happen better. But a little more advanced techniques might do that faster for us. One of them is just detonating it while monitoring everything. So we can use a sysinternals tool called procmon, right? And have a filter on it that says process name is WannaCry.exe and add that. Okay, yeah. So right now WannaCry.exe has not been detonated, so it's not really doing anything. Now let's detonate the malware again, and we see a flurry of events happening. It's a pretty big list, and it will probably take a while to go through. But basically, it does a lot of stuff. So we can filter further. Operation contains file, so we can see if it interacts with any file, right? Yeah. Okay. So it's probably importing all of these DLLs. That's all it's doing primarily. Now, since I have dissected this malware before, I can see that this .exe is here and there are no more exes, right? It's just calling the DLLs, probably importing them, but here it creates a file, right? Task sche.exe, and if we go into, let's say, Windows, the actual place where it is, we can, oh yeah, that was running. I forgot about it. That was like a jump scare, but there it is. So this is one exe which is now come out of the WannaCry executable. Moreover, I think it creates that, and it also interacts with the WannaCry executable. That's pretty much it. Rest of it is just calling DLLs, so no more file operations. I'm curious to see if there are any TCP operations. We can take a look. Probably not, because I have not yet added a proxy. Okay, there is. Oh, or wait, is there? Process name is WannaCry. Alright. So WannaCry has been trying to reach some place. WannaCry is sweeping my whole subnet. This is the subnet that I am on, and it's sweeping that whole subnet. Trying to, rather, to find another host where there might be eternal glue present, which it can use to execute some stuff, but it's not there. So yeah, it's doing a sweep. That's all the connect that we can see. So this is like one part of it, because what actually is happening in the background may not be understood that properly if we just do this, right? So we'll try to mimic a situation where maybe the internet is turned on, but I don't really want to turn on the internet, because then my computer might become a source of the attack, right? So in that case, what we do is we use something like fake net. What fake net is it mimics the presence of internet. So if you send a DNS query to it, it will respond. If you send an HTTP query to it, it will respond and give you a response, right? If you request a resource, it's going to make up a resource and give it to you, right? So we can actually understand what this particular malware is trying to do. So let's turn on FakeNet. Okay, so we can see a lot of stream is going through, and let's also run WannaCry again. Nothing's happening. I did run that as administrator. It's just not detonating. Why? Okay, let's see why. Let's get this stopped. Yeah. Let's look at the data it actually captured, right? Okay. This is a lot of data. Let's because we saw an HTTP URL there. Let's just look for HTTP communication, and we can see that the binary is trying to reach this host, right? And that's it. It's getting a response. Nothing further. Nothing further. If we just look at TCP, we might actually get some Microsoft stuff as well. But let's try to see this in an HTTP stream. We only have 2 HTTP streams, so that is that. But basically, we see that it's reaching out to this host, and if it's getting a response, it's not detonating, right? I'm not sure if it's going to capture the DNS queries as well. Yeah, so it did a DNS query naturally before doing an HTTP request. And when there was a response from this URL, the binary decided not to detonate, right? That's very interesting for me. With this, what I would do is move to a bit of advanced static analysis. Just tear open the binary, right? Let's open WannaCry. And the best thing about this is we can actually go ahead right now and see why this happened, and the fact that we could have known this without even running the binary, right? Moreover, there have been more there was more possibility of dynamic analysis, and we can find more host indicators. But we'll go through with a little bit of advanced static analysis, jump into dynamic analysis, and discover them on a more hands-on way, and not just looking at what all changed. So this is our main. Yeah, this is the flow. Okay. Now this is assembly, so it may be a little difficult to understand, but you can see this is the HTTP string over here, right? The one which we found earlier, and the one to which the request was going to, right? We move down a little. Let's just skip past the assembly. It's all right. We have to triage. We don't have to do anything else. But it calls internet open A, internet open URL A, and internet close handle. If we go to if we use the internet open A, right? It's a Win32 API function. What does it do? Initializes an application's use of WinINet functions. Okay, so basically it's gonna initialize your process of opening a URL probably, or using the internet. And if we do open URL A, what does that do? It opens a resource specified by a complete FTP or HTTP URL. And the syntax is, we have a handle to internet, which I think would have been found from this place, right, when we called this. Then the URL, headers, header length, flag, context. Okay, so this ESI, this since this is a syscall form, right? So all the Win32 API, how it's going to be called is that in assembly, how you can read it is internet open URL A. This is the first argument. This is the second, third, fourth, fifth, sixth, whatever, right? So ESI would, at this point, when the EIP is here, ESI would not probably, but will contain the handle which was created by Internet Open A, and this ECX counter would actually have the URL, this one, right? You see it being moved to ESI, probably over here somewhere. It's gonna maybe move in a different way, right? So basically we can deduce that. We're going to take a better look at this when we can actually read these registers while dynamically debugging it, right? So there is the first branch, and then it does this. Looks like a very simple if statement, like the flow is getting branched off into two parts. After closing, like doing the internet close handle, if the zero flag is not jump, this is basically jump if not equal to zero. No, jump if not equal, right? So what it's gonna do is it's basically essentially it's an if statement, right? If something happens, do this. If something else happens, or like else, go here, right? This block is effectively just ending the main, right? Because this is main. We're not inside a function. This is just ending main. So it's essentially not doing anything. Just by looking at these two blocks, this one and this one, we can deduce, and from our experience, that if we find a valid HTTP response from this particular domain, then we're going to exit, the malware is going to exit, it's not going to do anything. But if it doesn't, then what it's going to do is going to call a function, this particular function, 408090. We can make a mental note of this number because this is essentially where the malware starts its execution, right? It's been passed through that check. Now this flow is of the malware executing. Okay, so yeah, again there is a branching here for something, right? It does a module file name A. See, all of these are Win32 API calls. We can take a better look at them individually, but what essentially all of these do, at least on this branch, is open SC manager. Now this is something like Internet Open A. This allows you to have an interaction with the service manager, right? Open service A, close service handle, and then calling some functions, start service control dispatcher A. We actually will take a look at these particular Win32 API calls because they will help us understand what the flow is like, right? We still have these user-defined functions in the middle, which we'll have to go in and take an individual look. So open SC manager. Establishes a connection to the service control manager on the specified computer. Yeah, so just like Internet Open A, right? Like that's what I feel. Then we have Open Service A. what does it do? Opens an existing service. So this branch opens an existing service, right? Yeah, and there is this other branch which is user defined. So where my mind goes to is maybe the persistence mechanism is creating a service, and this particular branch is making sure that that particular service is being executed, right? Because we again have this particular Win32 API call called start service control dispatcher. What's gonna do? Connects the main thread of a service process to the service control manager, which causes the thread to be the service control dispatcher thread for the calling process. Okay, that's a lot of words, but this is essentially, I think what I feel is that this branch, what it's doing is it's ensuring that a particular service is being run. We have another user defined function here which we're going to take a look at in a while, but we have this particular function here on the left side, and let's go take a look. This particular function has two more functions in it, and then it returns, right? So once it returns, it has essentially ended this 408090, and once that ends, 408090, we go back to main, right? When this ends, the whole program finishes. Okay, so the first function, again a big one, we are creating a service. Okay, so the left side of the previous graph, this one, the right side is potentially ensuring a service is running an existing or interacting with an existing service, and the left one is creating a new service. And maybe this part, this branch is getting command flow when we are not able to open a connection to the service manager, right? So we're creating a service over here, and we have these comments over here which tell us exactly what each of these arguments are. The first has to be handled to the service manager, the second has to be a service name, right? And this is in string, so mssec service 2.0 display name this. All right, so this is essentially the service which is going to be there once we detonate malware. So we'll come here, we'll create a service, and I'll show you that while running the service, that's how it looks, right? So it starts a service, then it creates a service, it starts a service, it returns. Okay, that is pretty straightforward. That's all it's doing. It also has a this binary path name, which again right now it's a variable. So we'll be able to take a look at what this is once we do some dynamic analysis. All right. So that was the first function. Then there is the second function, which is creating a file. So while doing the basic dynamic analysis, we saw a task sche.exe being created. This might be what is doing this might be the code block which is actually performing that operation, creating a process, creating a file, writing a file. Okay, so these are strings. These are not being executed as of now, but we are calling variables. So that might actually be happening. We'll have to take a closer look in the dynamic analysis part of the things, because it's very tough to keep a track of variables while reading assembly, right? Assembly veterans will disagree, but for me it's difficult to keep a track, right? Find resource, load resource, lock resource, size of resource, right? So we have another string over here, which I think we'll see soon, because we also have this string over here, task sche, right? And we're calling functions back to back. Here we don't have the comments for what functions, because I think they are loaded dynamically to prevent easy static analysis. But don't worry, we'll get through with the dynamic analysis part of it. So it's creating this task sche here probably, and we also have this this string format, which we're gonna have to again take a look during dynamic analysis. But this has given us another indicator that we might also find a file there. Move file, yeah. Okay, it's probably moving a file or something, right? And the rest of it seems to be something like cleanup. Oh, we're still calling stuff, right? So that is pretty much it for this function as well, right? Okay. So that's the second function, then it's gonna return, right? So let's jump into to a debugger and see this. But before I do that, what I wanted to show was that using different decompilers actually might make a difference while you're trying to analyze malware. So if we take a look at the same binary through something like Ghidra, okay, then we might find that it has a different way of portraying stuff. Project name WannaCry. And the naming conventions that these debuggers use can sometimes actually help you understand what context the original code was written in. Let's analyze. Okay, we have some decompiles over here. Let's move to our entry function, right? And here, like we do see, I do see the similar kind of code like get module handle A, right? But the way it's portrayed here in a like decompiled and not in a graph form, that may not really be my thing, right? And when I create a graph like this, it's showing me exactly what's happening in a very interactive way, right? It's showing the code flow based on the results of this, like J and Z is jump if not 0, so it's checking for that variable. If the 0 flag is there, then go here. Sorry, if it's not 0, then go here, otherwise go here, right? So that's the code flow. But if I just take a look at this from a very take a bird's eye view on this, it has a lot of stuff which I don't understand, which don't really sink in, right? I can't just look at this and spot functions here, right? I can see functions being called here, going back and forth. I think it's a matter of personal preference as well. I'm not trashing on Ghidra, so if anybody loves Ghidra, sure, a lot of love to Ghidra. It's helped me in a lot of CTF challenges. But we see decompiled code here. Sometimes it's gonna make more sense when you see decompiled code rather than code flow graphs. So it's better to switch between debuggers and see which one is working out for a particular project, or which one is working better for you, right? You don't have to stick with Cutter just because I used Cutter. Let's open WannaCry in IDA as well, right? So here again, IDA has given us a graph. This is, I think this is almost the same as our Cutter, and instead of function, the convention here is called sub. So we can see the exact same flow: OpenSC manager, open service A, close service handle, and stuff like that, right? So we can see exactly what is being done the same way it was there in Cutter. I have a personal preference to Cutter, so I always have a bias because I started malware analysis on Cutter first. But Kidra is really nice. IDA is also amazing. And now let's not get carried away about with comparing decompilers, my bad, and let's head to some active debugging, right? So let's open WannaCry.exe in the debugger. Okay, a lot of panes here. A simple overview is this: in the top left, this particular pane, it's showing you the current assembly flow, right? This is the EIP, the instruction pointer. It's going to go down in this flow and execute these particular assembly commands. All the comments that you were seeing in the assembly code, or the values of what's in these particular registers, is visible on this sub pane, right? This is the assembly, as you can see. On this top right pane, we have registers. These are all the registers which the assembly interacts with, right? This over here is your stack, and this over here is dump. So we can actually follow anything to the dump and just see the whole value that is present there. Anyhow, so the code flow that we were interested in was 408090. Yeah. From here, our execution really starts. So I placed a breakpoint over here, and I let the program execute till it reaches this point. Now, technically, WannaCry.exe is running. However, it is still its execution is paused on this instruction. So we don't see anything pop up here like we did when we originally detonated it. So what we will do is we'll go through each like the whole process, the whole assembly commands. We'll go through them all, and if something unforgiving happens, we can always just reload an older snapshot and just get back into this. So this is that part where we have this is the function which was to the left, like in the original graph, which was towards the left. This is that function. So we'll step into it instead of stepping over it. If I do step over at this point, whatever this function is calling will get called, and whatever, like, this code flow will follow. But I want to actually go into what this function is doing. So instead of step in, I'll step over, I'll do step into. Now I can see these two functions here. I'll actually open Cutter as well, so we can keep track of exactly where we are. Right, so that was the entry point. This is the main. Yeah, so we were on this left branch. We had found, yeah. This is where I placed the breakpoint. I went through some of these instructions in a flurry and went to a function which is on the left side of the graph, and now it has two more functions. I can see that exact situation here because we're calling two more functions over here. So let's step into this and see what's gonna happen. So we have open SC manager A, right? So till here nothing major is gonna happen probably, and we're gonna get a handle to the service manager. So let me just, yeah, once this is called, there is this handle that is now available. What I want to do, yeah, is get to this create service A, right? Okay, so now we're gonna run create service A, and these are going to be the arguments, right? And let's just take a look at what create service A is gonna do and what arguments does it take. So it takes the handle, so this EDI would be the handle. It takes service name and then display name. So service name is going to be MSSec SVC 2.0. The display name is going to be Microsoft Security Center 2.0 service. Desired access is this particular variable. Desired start type, service type is 10. Start type is 2. If we go lower, we can see that start type 2, start type is 2 or service type, yeah. So service type was 10, right? Service type was 10. So it is Win32 own process, a service that runs in its own process. And the start type is 2. So it's an auto start. The service is started automatically during system startup. So that is its way of establishing persistence, right? And error control is normal, right? So it's not really doing much there. Moreover, we have this ECX over here, which is LP binary path name here. And that at this time is users analyst desktop WannaCry.exe-m security. When we create a new service, we tell it what exactly to execute, and this is what it's gonna execute every time the system starts up. So you have like this is an unrelenting way, relentless way of just maintaining persistence. And as soon as I get through with create service A, when I like call that service, we're gonna create a service. Right now it's not gonna be there. If we get into command prompt and do something like sc query msec service 2.0, that was the name, right? Sec service 2.0. The service does not exist as an installed service, but let's do 2 step overs, and now it exists. So essentially we were able to make sense of this assembly, right, and deduce that this sort of an activity is gonna happen. Now we're gonna close the service handle, and then this service is gonna start. So right now the service state was stopped. After this call, it's gonna start, and when this starts, it's gonna do a lot of things. So we'll have to destroy this whole thing and do this again. But as soon as this service starts, we're gonna see a lot of different things happening. Now the service has started. What that essentially does, like this is now running. So now WannaCry.exe-m security running as the system. Now it's gonna resume its own execution. Like I am still like I am still over here, right? But WannaCry.exe is running in the background as well. This is one instance of it, but there is another one that's back there and it's running. Now we have the second function. So this function is done. Now we have this second function. First function created and started a service. Let's see what the second one is aiming to do. Get module handle, get proc address. Okay. Call EDI. What is EDI? Is get proc address. So essentially how you can read this is it's calling EDI, and EDI has a value get proc address. So that is the Win32 API that's going to get called, right? Let's go over all these calls that are being done. Okay. I think I skipped a little ahead, but we basically ran a create file A, and we were supposed to look for, okay, no. I think I'm getting a little lost in the assembly. Yes, okay, so the task CHE is there, alright. So it's doing some stuff, it's creating some files. I'm not sure where, because I did not really see any more indicators at that point, but it's moving things to registers for creating processes. It's gonna probably call it later, right? Now it's gonna find a resource. If it doesn't, it's gonna, so now these JEs are basically jump statements. So you can see the branches go down, go out from it, right? Scroll, yeah, go out from it. So if this was an equal, like if this was true, it would probably not go towards the left, right? And that's how we are going through the whole assembly. We called this a load resource, called a lock resource. Still right here, still just getting through stuff. I think that's a little bit of cleanup. Now we're getting to the task che.exe, right, and sprintf. So that's probably gonna, what I see from these comments is this is a string descriptor. Like if you've written C, you know that these symbols can be replaced by strings when you're printing something, right? So that is essentially what's gonna happen most likely once this printf is done, like once I do this call. Yes, so now the ESP right here, it has this particular string in it, like it's there. Let's go ahead, we're doing another sprintf. So now it's probably gonna be C, Windows, and then this QERI and whatnot, as you can see here in ESP. Now we're gonna like move the ESP to some different places, right? Yeah, so we have reached a move file XA. The thing is that if we go and take a look at what move file does, it does exactly what it says. Move file XA. It moves a file, moves an existing file or directory, including its children, right? So, but there is not supposed to be a task CHE there. And as we can see, it's not there. Then how is it gonna move task che.exe to this file, to all or folder, right? How is that gonna happen? So we call that function, and I like to display the error stack here. Error file not found. Like this is not just a very cool thing to see in in malware, but in general we can use this debugger to actually debug so many of our programs that we write, right? So basically this particular command failed because task che was not there, right? And we move a little forward, and now we have a create file A, and we can go and look at what all of these mean, but essentially it's going to create this file because that's what the first variable is, argument is. So let it call that file, call that function. Is there something here? Okay, now we have this new icon here of an empty application that's here, right? So we can see that it's creating a task che.exe. We move further down and we have a write file. So somewhere along these lines, if we again take a look at write file, yeah, the write file function, it has the handle to the file, the buffer, the number of bytes to write. This buffer will essentially contain the contents of the file, right? Oops, yeah. So the first one, ESI, would have the handle. The second one, EAX, would have the buffer, the actual information to write. If we go here and follow this in the dump, the EAX value, we see like here, this whole thing, it's starting with MZ, right? And if you're more acquainted with the MZ magic byte, it's there for a portable executable. It's executable file format for .exe files. So it's gonna write something which is starting with the MZ magic bytes, hence a .exe. We know that because we know what the location it's writing to, but this is something that you can come here and observe in the dump. Anyhow, let's let it write. So currently it still should be at 0 bytes, 0 KB, and once I let it write and close the handle, we have a task sche.exe with some data, right? Okay. Now if you'll notice that there is still no detonation here, so what are we waiting for? Where is the detonation, right? So let's keep moving along, because now we're reaching a point where we're creating a process. Okay, I'll stop right here. Create process A. Create process A. All right. So the syntax has the application name, the command line, security attributes, process attribute, thread attribute, inherit handles, all sorts of stuff, right? Right here, yeah. So the first one, application name is okay. Wait. CBX, EDX. Okay, so they have done a little bit. I think the optimization has done a little manipulation here, but like the standard call, if you see, like here, right? This is the first. This is your first argument. So and rest of them are 0, 0, 0, and 8, 800, 8. Sorry, yeah, 8 something, right? So if I let this execute, some process has been created, and now we can see everything, detonating the way that it was. more interestingly, now even though this program right here, WannaCry.exe, it's still halted at one place, that task CHE has managed to encrypt my files and do the whole thing. So what we can assume or gather from this is WannaCry.exe is kind of like a persistence wrapper, which just makes sure that this task sche.exe keeps on executing, right? And like it does not halt and it properly runs. What task sche.exe does, like the malware analysis of that particular binary, is also something that we can do, right? And do drop it in chat or in a comment if you want to see me do a malware analysis on task sche.exe, because that is also one very interesting thing, because in the end that's what WannaCry, that's the actual cryptor, right? What we saw in all the assembly and all the decompilation and all the debugging was more of a persistence wrapper, right? That particular service is running, right? And right? And yeah, see, the binary path name is that. So the point of the whole debugging is we know that this is going to happen before it happens, so we know where to look for indicators, right? We can also do this by having a very in-depth analysis of procmon, but I find this way to be a little more fast and a little more simple. So that will be it for the stream. WannaCry is a very, very big rabbit hole that I have fallen into before, and it's very interesting to take apart and decompile. However, it takes a lot of time to get through all of that, and we can do that in another live stream if you guys want. So again, just comment down if you want me to dissect task sche.exe, or if there is another piece of historic or interesting malware out there which you wanted opened up for you, because we can definitely do that. That is something very interesting, right? Anyhow, that will be it for the stream.